All right, welcome to our very first session on dynamic topology. We're going to be using Gordon Whyburn's classic text as our guide. And the idea here is to build everything from the ground up, one foundational piece at a time. I absolutely love this quote from the foreword. It just perfectly captures the spirit of what we're trying to do here. We're not going to just sit back and watch mathematics happen, right? No. We are going to do it. We're going to get our hands dirty. We're going to build proofs and really, really get a feel for these ideas, almost like we're students in Whyburn's original classroom. So here's the game plan for today. We're going to start with the absolute basics, the alphabet of sets. Then we'll dive into this pretty mind-bending idea of different sized infinities. And finally, we'll take our new tools and use them to prove some really foundational stuff. It's all about getting our toolkit ready for the adventures ahead. Okay, let's get into it. Before we can start exploring all the weird and wonderful shapes of topology, we first have to understand the bedrock that everything is built on, and that is the concept of a set. Every field has its own language, its own vocabulary, and for us, that language starts with sets. These are our fundamental building blocks. They might seem like simple ideas, but trust me, they are incredibly powerful. So, what is a set? I mean, logicians can spend their entire careers on a super rigorous definition. But for our purposes, it's actually beautifully simple. A set is just a collection of things. You can think of it as a bag of stuff. The numbers 1, 2, and 3, that's a set. All the books on your shelf, that's a set too. And if some object X is in that bag, we just say X is an element of the set A. Simple as that. Now, if we've got two sets, we can start to talk about how they relate to each other. If every single thing in set A is also in set B, then we say A is a subset of B. It's really just an idea of containment. The set of all poodles is a subset of the set of all dogs. Makes sense, right? Okay, so we have our basic objects, our sets. Now we need some verbs. We need some rules for how these sets can interact with each other, how they combine, how they change. This is what we call the algebra of sets. The two most basic actions are union and intersection. The union of A and B is basically everything that's in A, or in B, or in both. Just think of it as dumping everything from both sets into one big collection. The intersection, on the other hand, is a bit more picky. It's only the stuff that's in both A and B at the same time. And then there's the complement. The complement is just everything else. For instance, if our universe is all the integers and set A is all the even numbers, then the complement of A is, well, it's all the odd numbers. It's simply everything that's not in A. Now, what's really cool is how these operations follow rules that should feel kind of familiar. Just look at this. They obey distributive laws, just like multiplication and addition from back in school. Union distributes over intersection, and what do you know? Intersection distributes over union. It's this reliable structure that lets us build some really powerful arguments. And this is De Morgan's laws, which are just so elegant. It shows this amazing symmetry. If you take the complement of a union, it's the same as the intersection of the complements. And if you take the complement of an intersection, it becomes the union of the complements. See how the operations just flip? It's an incredibly useful tool for simplifying complex logical ideas. Okay, now that we have the rules of the game, let's ask a question that really turned mathematics on its head. How do we measure the size of a set? I mean, it's easy for finite sets, you just count. But what about infinite sets? As we're about to see, not all infinities are created equal. So we call a set countable if we can, at least in theory, list out every single one of its members. Now, that list might go on forever. But as long as you can point to a first element, a second, a third, and so on, in a way that you know will eventually get to every single item, then that set is countable. The positive integers are the perfect example of this. And here is where it gets really good. With just these few simple rules and definitions, we can actually start to prove some really deep, really surprising things. We're officially moving beyond just defining terms and into building real mathematical arguments. So here's our first big question. Let's say I have a countable number of these listable sets. So an infinite list of infinite lists. If I smoosh them all together, is the resulting collection still something I can list out? I mean, it feels like it should be way too big, doesn't it? Well, the answer, kind of surprisingly, is yes. it is still countable. And this slide shows the incredibly clever proof. We arrange all our sets as rows in this giant grid. Now, we can't just count row by row because we'd never even finish the first one. So instead, we snake through the table diagonally. We take the first one, then the one over, then the one down. We go a 1-1, then a 1-2, then a 2-1, then a 1-3, and so on. This diagonal path absolutely guarantees we eventually hit every single element, which proves the entire collection is countable. How cool is that? Okay, so we know the integers are countable. It turns out the rational numbers, all the fractions, are also countable, using a pretty similar trick. But what about all the numbers? The real numbers, including all the irrational ones, like pi and the square root of 2. Can we make a complete list of all the real numbers, even just the ones between 0 and 1? We're going to tackle this with one of the most famous arguments in all of mathematics, a proof by contradiction, from the brilliant mind of George Cantor. The way this works is we start by assuming the exact opposite of what we're trying to prove. So let's just assume for a minute that the real numbers are countable, that we actually can make a complete list of them. So if we could make that list, it would have to look something like this, right? The first number, A1, has its own decimal expansion. The second number, A2, has its own unique expansion. And this list, according to our assumption, goes on forever and contains every single real number between 0 and 1. It is, hypothetically, complete. Now for the genius move. We're going to build a brand new number, let's call it R, that is guaranteed not to be on this list. And here's how we do it. For the first decimal place of our new number R, we're going to look at the first digit of the first number on the list, and we just pick any digit that's different. For our second decimal place, we look at the second digit of the second number and pick a different one. We just keep doing this all the way down the diagonal, building our number piece by piece. So here's the killer question. Where is this new number R on our complete list? Well, it can't be the first number, right? Because we deliberately made its first decimal place different. It can't be the second number, because we made its second decimal place different. In fact, for any number you pick on that list, say the nth number, our new number R is going to be different from it in the nth decimal place. And that is the beautiful contradiction. We've managed to construct a real number that, by its very design, cannot possibly be anywhere on our supposedly complete list. So what does that tell us? It means our initial assumption that we could make a complete list had to be wrong. It was impossible from the start. It is fundamentally impossible to list all the real numbers. They are uncountable. This is huge. It proves there are different sizes of infinity. And the infinity of real numbers is just mind-blowingly bigger than the infinity of the integers. So we've done it. We've established our fundamental language. We now understand what sets are, how they operate, and this profound difference between countable and uncountable infinities. We've got our basic toolkit. Now it's time to start building something with it. And that leads us perfectly to the big question for our next explainer. So far, we've just been talking about collections of points, kind of floating around. But what happens when we add some structure to them? What happens when we define an idea of closeness or neighborhood? What does it really take to turn a simple set into a topological space? That, my friends, is where the real fun begins.